Welcome to lecture number 15 for ECE 341 Random Processes. In this lecture, we're going to look at the exponential distribution. Now, an exponential distribution has the following PDF. It's a e to the minus ax for x positive and 0 for x negative. Now, this is another common distribution which appears over and over in nature. For example, the length of a telephone call is an exponential distribution. Most of them are fairly short, but a few of them can be really, really long, and there's no upper limit. It goes out to infinity. The time until an atom decays is an exponential distribution. The time it takes for the next customer to arrive is exponential. The time it takes to serve a customer is exponential. So this is a little bit different than a uniform distribution. The uniform distribution just took on a fixed set of values, like between 0 and 1. An exponential goes out to infinity. Probability gets smaller and smaller, but there is no upper limit to how long it could take. Exponential distributions also lead to queuing theory. Queuing theory looks at a restaurant. If customers are arriving with an exponential distribution and the time it takes to serve a customer is exponential, how long is the line going to be? How long are customers going to have to wait to get served? That matters in business because if the line is too long, people turn around and leave. That's lost revenue. If the time it takes to serve a customer is too long, people get frustrated, leave. That's also lost revenue. So I want to keep the queue size short, the wait time short, but I also want to minimize the number of people hired to serve the customers. So that's the idea of queuing theory. We'll look at all that during this lecture. Now the PDF for an exponential distribution is a e to the minus ax. The CDF is the integral of that. That is 1 minus e to the minus ax. You can kind of see that in MATLAB. So this is the integral of an exponential. The exponential is in pink. This is 1 over s sweeping to the right. And what I have here is convolution. The area is the red line. That is the integral of the PDF between 0 and x. And as I sweep to the right, I catch more and more area. Eventually, I'll catch all the area, and the CDF goes to 1. It never reaches 1 from an exponential distribution, but it approaches it. So this would be an exponential distribution with a mean of 2 seconds. If the mean is 1 second, it looks like this. I start to pick up area at t equals 0. The red line gets higher and higher, and again it approaches 1. So here the average is 1. The maximum time is infinity. It's exponential, but the average is 1 over p. So that's an exponential with a mean of 1 second, PDF and CDF. To make the average, say, 4 seconds. Here's the PDF in pink. The CDF is in red. So here I sweep 1 over s to the right. That's your convolution. As I sweep to the right, I catch more and more area. And eventually, I get to 1. So here the average is 4. The PDF never quite gets to 0. The CDF never quite gets to 1. So that's an exponential distribution, the PDF and CDF. This is where moment generating functions are really useful. If I have this function and I want to find the average, that's actually kind of hard because this goes out to infinity. So finding the mean, the variance is difficult with the PDF. Can be done, but difficult. It's actually easier using the Laplace transform or moment generating function. So the Laplace transform is called the moment generating function because you generate moments with it. The 0th moment has to be 1. That's the total probability. In statistics, all probabilities sum to 1. So if I plug in s equals 0, I get a over a, or 1. This is a valid PDF. The mean is the first moment. The first moment is the derivative of the PDF as s goes to 0. So the derivative of a over s plus a is a over s plus a squared. Plug in s equals 0, I get 1 over a. So the mean of an exponential distribution is 1 over a. So likewise, on this graph, a was 1/4. The mean is 4. The variance comes from the second moment. Take the derivative of the first moment, and I get 2a over s plus a cubed. Plug in s equals 0, I get 2 over a squared. The variance for continuous time systems is the second moment minus the first moment squared. That's 2 over a squared minus 1 over a squared gives me 1 over a squared. So that's the variance of an exponential distribution. This will be important later on. When you add distributions, the means add and the variance adds. So if I ever want to find out what happens when I have two exponentials added together, or uniform plus an exponential, the means will add and the variance will add. That's kind of where we'll do this. We'll use that later. So to generate random variables with an exponential distribution, this is where the CDF is useful. The CDF is probabilities between 0 and 1. I'll take the probability and map it over to the CDF. That tells me what x is. So the CDF is 1 minus e to the minus ax. If I know the probability, call it p, then x is going to be subtract 1 on both sides, flip the sign, 1 minus p. Take the log, divided by minus a. That's the variable with a exponential distribution. Pick a random number for p and calculate x. So suppose I have a mean of 1 second. Then generating 10 random variables with an exponential distribution with a mean of 1 second would be as follows. Generate 10 random p's. For each one, take the log of 1 minus p times minus 1 over a. That's x. And when I do that, if I plot x and p with a dot, that's my CDF that I'm getting. P is a uniform distribution between 0 and 1. X is an exponential distribution. And that's actually kind of a nice way of doing it. So for example, in MATLAB, go over to MATLAB. Let's have P, do 10 random numbers. This will be an exponential distribution with a mean of 4 seconds. So x is phase 1/4. X is minus 1 over a times log. MATLAB log is log base e. Log 10 is log base 10. Log of 1 minus p. That is 10 random variables with a mean of 4 seconds. If I want to do 10 seconds, that out. Ten random variables with a mean of 10 seconds. And notice occasionally it's very small. The smallest it can be is 0. The biggest can be is no limit. Here the biggest number got is 45, 26, 20, 29. Again, for an exponential, the probability, well, it could go out to infinity. The probability gets smaller and smaller, but there is no upper limit to how large the number can be, like there's a 68. That's an exponential distribution. Here's an example of that. Suppose I have a block of radioactive material. It's sitting next to a Geiger counter, and in 30 minutes, the Geiger counter detects 100 atom decays. Determine the PDF and the CDF for the time until the next atom decays in minutes. Well, the solution is to find the average number of decays per minute. I've got 100 atoms decaying in 30 minutes. It's typically 3.33 atoms per minute. That's on average. That's 1 over A. A is 0.3. So the PDF is just 0.3 e to the minus 0.3x. The CDF is 1 minus e to the minus 0.3x. In MATLAB, I could plot that. Let's just have x go from 0 to infinity. I'm not going to go to infinity. Let's just stop at 20 seconds. The PDF is 0.3 e to the minus 0.3x. The CDF is 1 minus 0.3 times x. Plot the two together. Here's the PDF. Here's the CDF. So that's kind of about all you can do with exponential distributions. They're pretty straightforward. One application of exponential distributions is queuing theory. This deals with restaurants. When customers arrive, they typically arrive with an exponential distribution. The time it takes to place an order or serve an order is also an exponential distribution. What I want to know is how long are customers going to have to wait in line to get served? How long is the queue going to be? How long is the line when they get there? This is important because if the wait is too long, customers get frustrated and leave. If the queue size is too long, people walk in the door, see a huge line, turn around and leave. That's lost revenue. I want to keep the waiting time small, and I want to keep the queue size small. But then I also want to minimize the number of people I hire to work the cash registers. So if the queue and waiting time is small enough, I'll start telling people at the cash register to take other jobs. If it's too long, I'm going to reassign people to work cash registers, trying to keep those two numbers under control. So let's do that. Suppose let's do a simulation where customers arrive with an exponential distribution, and the time it takes to serve is exponential with an average of 30 seconds. Arrival time is 1 customer every minute on average. Well, I can do that in MATLAB. What I'm going to do is first keep track of a bunch of variables. Here's when the customer arrives. Here's when the customer is actually served. I'm going to have to wait in a line. When they finally get to the front of the line and place their order, this is when they're served. This is when the order is completed. That's the time that they place the order, plus the random time with an exponential distribution with a mean of 30 seconds. That's when they're done. How long they wait is the difference between when they arrived and when they actually got to place their order. And the queue size is how many people were in line. Let's start out with those variables, and let's bring in the first customer. When the first customer arrives, that'll be an exponential distribution with a mean of 60 seconds. So that's this number. When the first customer arrives, first customer of the day, there's no wait. They're served right away. There is no wait in line. There is no queue size. When they're done is the time they place their order plus an exponential distribution with a mean of 30 seconds. So there's my first customer. Now if I try that in MATLAB, get that part of the code to work. So here I am, the first customer arrives, 60 seconds, 30 seconds. Here's when the customer arrived. That's when they finished their order. There is no waiting in line. There is no queue size. Okay, so that looks like that's working. I've got the first customer simulated. Let's bring in the next 5 customers. Now for the next n customers, let's start with n equals 5. The arrival time will be the time the previous customer arrived plus an exponential distribution with a mean of 60 seconds. The time that customer places the order or is served is the maximum of the time the previous customer is finished and the time that customer arrived. So for example, the customer arrived at 31 seconds, nobody was in line, they're served at 31, finished at 50. Next customer arrived at 45 seconds. When that customer arrived, the previous customer wasn't done yet, so I'm not going to get served until I get to 50 seconds, until the previous customer is finished. That customer finishes at 83 seconds. Next customer arrives at 130 seconds. The previous customer was finished, so I'm served right away. I finish at 145. Next customer arrives at 140. The previous customer wasn't done until 145, so that number appears over here. I'm done at 166. Next customer arrives at 146. I'm not served until the previous customer arrives or is done, 166. So that's what this one is. It's the maximum of the time that I arrive and the previous customer. Now the time that I'm done, same as before, is the time that I'm served plus a random variable with a mean of 30 seconds. Let's get that to work. So in MATLAB, I've added this section code. I'm going to go to the next 5 customers. Here's when they arrive. This is when they're served, which is the maximum of their arrival time in the previous customer, maximum of their arrival time in the previous customer, maximum of their arrival time, previous customer, and so on. I can actually do this out for 10. About 15. 10. So I've got the arrival times working. I've got the time that they're served working. Again, this is going to be the maximum of the time that I arrive when the previous customer is served. Now that I've got that debugged, let's work on the wait time and queue size. Now the wait time is the difference between when I arrived and when I'm served. For example, there's no wait time here, no wait time. Here, I waited 53 seconds. Here, I waited 26 seconds and no wait time. That's the wait time, difference between when I place my order and when I arrive. The queue size is counting. As I arrived at 141 seconds, how many previous customers were still in line at the time that I arrived? Here there are 2 of them, so the queue size is 2. So to calculate that, the wait time is just the difference between the 2. The queue size is the sum. How many customers are done after my arrival time? And I get 2 in this case. 1 here and 2. Let's get that code working. So I add in the wait time and queue size. Let's go for 15 customers. When I did that, here, these are the wait times. The longest wait was 68 seconds. The largest queue size was 3. Let's try that again. Longest wait time. Let's scale by 1,000. Was 116 seconds. Longest queue size was 3. Longest wait time, 83 seconds. Largest queue size was 2. Okay, once I get that working, I can then let it run longer. For example, here's for 30 customers. Here's the arrival time when they're served. The wait time, there's the maximum wait time. When they're done, maximum queue size. That's kind of what I look at. If these numbers get too large, that means I need to reassign people at the restaurant and have more people work the cash register. If they're small, I might reassign some people to the cash register to do other jobs. That's kind of what a manager at a restaurant does. They're always watching the queue size and wait time. So once I do that, I can do something like for 200 customers, let's look what happens. So in this case, let's go for 200 customers, run the simulation. See the maximum wait time, Max wait time is 282 seconds. That's pretty long. That's almost 5 minutes. And the largest queue size was 7. So this is going to tell me that I am having problems keeping up with demand. I might need to bring in more servers. More servers will reduce the time to complete the orders, reduce this number. On the other hand, if it's small enough, I might reassign people at the cash register, makes this number bigger. So that's kind of what you look at with restaurants. That's queuing theory. And with that, you can kind of see the effects of the service time versus arrival time. If the service time is longer than the arrival time, I have more customers arriving than I can handle. The wait time increases without limit. So here, customers arriving every 60 seconds. It takes me 20% longer, 72 seconds to complete each order. So I'm falling further and further behind. What I need to do is bring in more servers, reduce the time it takes to fill the orders, or hire more cooks. If it's 80%, that's the purple, I'm keeping up, occasionally gets fairly large. If the time to fill the orders is only 40% of the arrival time, the queue size stays fairly small. So these are kind of studies I can do with the service time versus arrival time. If I look at the queue size, again, if I'm placing orders slower than customers arriving, the queue size, in theory, increases without bound. That's kind of bad. If it's 80% of the arrival time, I'll usually keep up. Occasionally, it can get fairly large, like here the max queue size was about 8. If I have my service time is 40% of the arrival time, the queue size remains fairly small. The biggest it got was about 4. That's queuing theory. This is all based upon the exponential distribution. So one type of distribution is exponential. It models many different types of systems, like the time of a telephone call, time until an atom decays, time until the next customer arrives at a restaurant, things like that. Exponential distributions lead to queuing theory. That's used to determine the expected wait time and queue size in stores and restaurants, something you study as a business major. All comes from statistics and exponential distributions. So with it, that is lecture number 15 for ECE 341, Exponential Distributions.